Hi, I'm Dr. Bones. This is my associate Skelly Skeleton. Hey, how are you? Skelly Skeleton here. It's the Dr. Bones Show. Hey, so we're going to be talking about more chemistry, the periodic table, and so on. Skelly, you got any periodic table jokes? Hey, I've got one about sodium. Sodium said he lost an electron, became sodium plus. Well, how do you know? Because he said he was positive. Okay, so sodium plus is positive. So he lost an electron and he became positive. Why don't you show them your eyes here? He's got his sunglasses on here. Okay, here you go. Here he is with his sunglasses off. So he'll be coming up in different episodes. He likes to tell his chemistry jokes and so on. What's the one about helium again? The helium atom. What's a female helium atom? I don't know. What's a female helium atom? A helium. Okay. I think that's enough for now. All right. Let's get the sign down here, and we will be putting up the periodic table. In another episode, we were talking about molecular geometry and bonding and so on. I'm going to put this up here a little bit more. So we've got our periodic table here, a small one, and a larger one over here. I'm going to be going over to the various groups. We mentioned the first group, group 1A. These are the alkali metals, except for, of course, hydrogen. Hydrogen behaves like the alkali metals. It has one outer shell electron, very reactive. Group 2, group 2A, the metals concerning magnesium and calcium, beryllium, strontium, barium, and so on. Transition metals, we talked about a little bit before, various oxidation states. So +1 here with the alkali, alkaline earth, +2, various oxidation states for the transition metals. Oxidation states are important in bonding. We come back over here all the way to the closed shell group. This is group 8. So we have 8 electrons in the outermost shell. Helium, neon, argon, krypton, xenon. These we call the noble gases, rare gases, inert gases. They don't like to bond to each other, right? So we're not going to see helium dimers or neon dimers under normal conditions. The group 7B, fluorine, chlorine, bromine, iodine. -1 is the charge because they have 7 electrons in their outermost shell and they'd like to behave like the inert gases, so they'll be able to accept an electron and be a -1 charge. Group 6, group 5, group 4, group 3, and so on. We're going to be talking about the oxidation states and bonding and so on when we go to Lewis structures. Today I wanted to talk a little bit about hybridization and molecular orbital theory. So before we start, I just wanted to mention some of the elements in the periodic table. So -1, -2, -3, -4. However, these, depending on their electronegativity, can also be plus charged, all right? So the most electronegative is fluorine, all right? So when nitrogen bonds to fluorine, fluorine will be minus charged, nitrogen would be plus charged, all right? So we'll be discussing this in other lectures. All right, so let's go back over here. Wanted to talk a little bit about hybridization. We mentioned this before. We have different types of orbitals. S orbitals, p orbitals, d orbitals. The s orbital is simply a sphere, all right? So an s orbital is simply a sphere. We talked about the p orbitals, all right? So the p orbitals look sort of like a figure 8. So kind of a, whoops, come back here. All right, so sort of a figure 8 shape. And you would be putting these types of figure 8 shapes together to form d orbitals, all right? And you can use the orbital structure to construct molecular shapes. So in terms of molecular shapes, when we put s and p orbitals together, we can form linear molecules, sp2 bent, sp3 tetrahedral, trigonal bipyramidal sp3d, octahedral sp3d2 hybridization. And we were using pipe cleaners as an example. So an sp hybridization would be a linear molecule. So if you have a pipe cleaner, you'll simply have a linear pipe cleaner, all right? And if you wanted to, for example, put together other shapes using the pipe cleaners, have this black backdrop because the pipe cleaners are white. So you've got this sp2 would be a bent shape, all right, an angular shape, so sp2 hybridization, so using one s orbital and two p orbitals, and so on and so forth. If we wanted to put together, say for example, triangular trigonal shapes, this would be the trigonal formation. You'd have a central atom, and then you'd have three atoms in the periphery. We're talking about bent shapes, in this case trigonal planar. And we would continue this process. Here we have a square planar, right? So we have a central atom, and we have four peripheral atoms, all right? Those would be attached to the central atom. A tetrahedral shape here. And I've got a nice looking tetrahedron. So here we have the pipe cleaner version of the tetrahedron, all right? And so on and so forth. Okay, let me go over here and get a couple of the other shapes. Okay, I've got the trigonal bipyramidal shape, all right? So we've got a trigonal bipyramidal shape here with the pipe cleaners. So you see the trigonal formation, right? So you've got the three atoms, right? The planar structure, trigonal, and the two axial atoms, right? So a central atom and two axial atoms. And finally, the octahedral shape. So you've got 6 positions for peripheral atoms. Central atom here, we talked about this before, it's called octahedral because if you were to connect each of these points, you would have one face of an octahedron, all right? So this is called the octahedral shape. 6 potential atoms in space surrounding a central atom, but we call it the octahedral shape because it's from the octahedron. All right, so let's go back to some models like this. Be easier to play with. Because I don't really know if I need the backdrop here, but let's go back. I'm going to take this out, and you can see that this is our basic trigonal planar shape. All right, so here we start with our trigonal planar shape. Okay, and I'm going to add, in this case, we are going to require a d orbital. All right, so we've got a d orbital necessary for this particular shape. And I have the, put this back on here. All right, so we've got the trigonal bipyramidal shape. So here we've got the equatorial positions and the 2 axial positions. All right, so you can do these with the styrofoam balls as well. These are kind of neat. Got a wire here, strong wire, and also some wooden dowels. All right, and we can start with something like this. I am going to take off these axial atoms. So we're starting with the square planar structure, all right? Here we're going to need 2 d orbitals to put together the octahedral. All right, so this would be sp3d2, whereas the trigonal bipyramidal would be sp3d. All right, so we would be using various sp and d orbitals for these structures. So here's the octahedral structure with the styrofoam balls and the wire. All right, so those are your molecular shapes from the hybridization method. Finally, I wanted to do have a little fun with some color solutions. We've got representing either the s or p orbital. we are going to use yellow and blue and show you when you create these hybridized orbitals, they are neither S nor P, they're a combination. So I've got my test tubes here. What I'm going to do is put some yellow colored water in 3 of the test tubes. In this case, they're going to represent the p orbitals, so I'm going to construct an sp3, so s and 3 p orbitals. All right, so here I go. A little bit more here. I suppose in the end you can kind of zoom in when I get these filled up. So here's the 3rd p orbital. For example, when I put together a tetrahedral shape like this, you would have in methane carbon in the center and 4 hydrogen atoms. Well, in this case, the carbon is using its s orbital and 3 of its p orbitals so that the 1s orbitals of each of the hydrogens can be utilized. All right? So I've got my 3 p orbitals, and now I need my s orbital. So here we go with the blue liquid. So it's easy enough to see the blue and the yellow. But again, these are not hybridized orbitals. If you zoom in here we're simply representing, in fact, if you want, I can reverse this. Let's just put it over here like this. We're going to have S and 3 P's. We're going to mix them all together to form the hybridized orbital. Right? For example, the man and the horse together is the centaur, right? The mythological centaur. So we've got S and 3 P's. Well, what happens when we mix them all together? We form something that's different. So here we go with our 3 p orbitals. Okay, and then finally we mix in the s orbital. We're no longer seeing blue or yellow. Now we've got a greenish color. So the hybridized orbital is not S, it's not P, it's sp3. All right, so we started with blue and 3 yellows. Now we're at a new color, green. So the hybridization can be similarly represented like this. All right, so kind of a fun way to demonstrate hybridization. Not blue, not yellow, but new, green. All right, I'll see you in the next segment, The Dr. Bone Show. Take care, bye for now.